Okay, then now we will talk about the induction motor, right? The induction machine can also be operated as the generator and motor as similar to other electric machine, right? Induction machine. We can operate it as generator. That means we drive it by mechanical power and we get the electric power with this machine. And with this machine, we can supply the electrical power and then we get the driver, the mechanical power output, right? Then operate it as the motor here. Okay, but I will talk about the operation of induction machine in motor mode. Right? In motor, use it as the motor because a very rare case that we use induction machine as a generator. For example, we use it in wind turbine power, wind turbine power, wind turbine like this, right? The induction generator is here. The induction generator is operated in the wind turbine usually, and not very popular used in the industrial and in power plant. In power plant, usually we use synchronous generator, synchronous machine for generator, and very rare case that we use synchronous machine as a motor also because we need to supply both DC and AC is complicated for operate as a motor, but it's very good for control when we use it as a generator. But in contrast, for induction machine, it's very convenient to use as a motor, and it's very difficult to use it as a generator because it is difficult to control the frequency, right? To make it operate at the constant frequency, frequency. For example, 50 Hz is difficult to control, and it's difficult to get the reactive power output from this type of generator. Okay. Therefore, in industrial, we usually use the induction machine as the induction motor, and we have both induction motor in 3-phase design and in single phase design, right? And I will go in detail only 3-phase induction motor that widely used in industrial. For single phase induction motor is also used, but a small one, right? Usually we use for small. And it's household use, for example, in your electric fan, right? In the air condition, right? In air condition, like for example, single phase, right? And it's usually small one. So for the large 3-phase induction motor is the topic that I will make today. Okay. So for 3-phase induction motor, in the presently motor is the machine used in general industry, and it is because the motor can convert electrical energy into mechanical energy, and the price is cheap. This is not very expensive one for this type of machine, right? We just and it's very convenient. We just supply the electric to this type of machine and it will drive. It depends on we connect it to drive something, right? For example, it can connect to pump or conveyor and etc. So anything that we need to drive. Okay. In practice, the motor can provide almost constant speed. So this type of motor is almost, but not exactly constant. When you load the motor more, right? The P output, we drive the with output. This is speed, right? Speed is almost constant, but it's a little bit drop when you when the motor drive the higher load, right? Yeah, just almost constant but not constant, which is suitable for industrial and the other application. It can be said that almost 30% of electrical energy used is in induction motor. If you walk into the industry, in the factory, any factory or any plant, when we see the motor, we can assume that motor is induction motor. Okay, exactly. So for the three-phase induction motor, Nikola Tesla proposes an idea to make magnetic field as the stator, right? And the rotor is able to rotate without DC supply to the rotor coil. For synchronous machine, we need to supply the power to the rotor also. But for induction machine, we just make the magnetic field induced into the rotor, and it will cause the force, right, the torque applied to that coil. Okay, here is the structure of the induction motor. We have two main parts. The first part we call stator, is the coil that produce the field. Here, the stator will provide the field, rotating field. The magnetic field that rotate around this, When we supply AC voltage to this coil, it will build the excitation field or rotating field here. Okay. Yeah, we call stator winding, usually in three-phase winding, and another part is the rotor winding here. Rotor winding, we have two types of rotor winding, which is wound rotor, is as a coil. Another type is squirrel cage rotor. By its shape, the squirrel cage is the conductor bar here. It's the bar that. And we have end ring to short at the end of this cage, right? It looks like the cage for squirrel, right? Squirrel cage rotor. We have two types. The most popular type of rotor is squirrel cage rotor. Here, squirrel cage rotor. Here, right? It's a conductor bar here. So when the stator produce the rotating magnetic field, it will cause the current flow, right? The current will flow in this bar, and by shorting at the end, the current can be flow in the circuit, right? And with magnetic field moving and the current flow in the conductor, therefore the force applied. There is the force applied to this conductor. Then the rotor will move, right? Will rotate here, right? If we see the front side view here, right? We have the coil in the stator, right? Like this. This is the coil in the stator. Usually we have three phase, right? Phase A, phase B, and phase C. We have three phase. We build the rotating magnetic field here, and this is the rotor. Rotor will turn around in the same direction with rotating field. Yeah, but the rotor will rotate in the speed slower speed than rotor has slower speed than magnetic field, right? Magnetic field, the rotating speed of magnetic field, then the rotating speed of magnetic field. This is because if the rotor turn in the same speed with magnetic field, the current will not flow in the rotor, right? Because the current is take place because the field, the magnetic field flow through this conductor, right? When you have the conductor with the magnetic field, right? The change of magnetic field will cause the current flow. Then the current flow in the conductor that stay in the magnetic field, the force is stay. Okay, then the rotor will rotate in the same direction with rotating magnetic field, but slower speed. For example, if rotating magnetic field speed maybe 1500 round per minute, right? Round per minute. The rotor may rotate in the speed a little bit slower than 1500, maybe rotor speed maybe 1450 pm. For example, the speed is a little bit different, right, between rotating field and the rotor field. The rotating magnetic field is constant by electrical frequency, right? Electrical frequency. For example, 50 Hertz or 60 Hertz, right? In Thailand, we have 60 Hertz, right? Electricity is constant by the frequency. We produce this speed, right? This speed never change because it's the magnetic field caused by electricity, right? But the rotor speed may change. Rotor speed can be a little bit changed. If you take the higher load, maybe the speed is lower than much lower than magnetic field speed. We can call the rotating magnetic field speed. This speed maybe we call NS or synchronous speed. Synchronous speed. The speed of magnetic field is constant. We call synchronous speed or NS. Okay. And the speed of rotor we call NR. We can call it the rotor speed, usually lower than synchronous speed. Okay. So for example, if we have this is maybe load, right? Motor load P out. We take P out in kilowatt. Yeah. This is speed, right? For NS, it's never changed. But for NR, maybe it's drop, right? It's drop. Maybe one NR is drop when we take higher load, right? So if we see the motor that's the operate at very low speed than its latest condition, it means that motor may be under overload condition. It's very difficult. It's very dangerous, and it's maybe burn the motor, right? With high current, with the heat, that the heat will not dissipate to the ambient around the motor because it's not rotate, right? Okay. The induction motor have structure which can divide into two major that I have talked in last slide: stator and stationary part, rotor and rotating part, right? The stator of electrical inductor is identical to synchronous motor. Okay, similar to synchronous motor, but we didn't talk about synchronous motor, right? And the structure of the rotor will be different, obviously. The structure of the rotor and in an induction motor will be one of squirrel cage or round rotor. Squirrel cage or round rotor. Approximately 90% of induction motor will be a squirrel cage motor. This type of motor is very popular and widely used in the industrial. Okay. This is because it's durable and easy. Easiest, right? Simple, right? And easy to use. Okay. Okay, the rotor structure of squirrel cage consists of rotor axis, rotor coil, and cooling. Okay, here, the cooling part, right? Fan brace, this is for cooling, right? And sometimes motor will have this fan itself to connect to the shaft, right? It will have the fan for ventilation to itself. Okay. Okay, I'm not going to detail this of this slide. I think you can read this is just the detail of the structure of the rotor. Okay, and this is the valve rotor. The valve rotor will have maybe difficult to operate. We need some slip ring and the resistance outside the motor to control. Here is slip ring for valve rotor. So therefore, the valve rotor is not widely used in industrial because it's more difficult to use, right? It's for squirrel cage. We just supply the electricity to this motor and it will move, right? It's simple. It's easy to use, right? Okay, for three-phase induction motor, the synchronous speed will be depend on the number of pole, the magnetic pole here, magnetic pole of the motor, or P, we call it here P, number of pole, and the speed of the motor can be computed by the synchronous speed is equal to 120 into the frequency of the supply electricity. For example, 50 Hertz, right? This is number of pole, and the number of pole is usually in even number, right? We can have 2 pole, 4 pole, 6 pole motor, right? Or any. So the lower number of pole is mean the speed is higher, right? Because the speed is higher. So the more pole motor, the speed is lower here. For example, if we have 4 pole motor for 50 Hertz, right? The synchronous speed of this motor would be 120 into 50 divided by 4, and it's equal to 1500 RPM, right? It means that the rotor will operate a little bit lower than maybe 14 something RPM. This is 4 pole motor. For 2 pole motor, it will be 3000 RPM for synchronous speed, and this type of motor will operate maybe 28 something, right? 28 something RPM NR, or 29 something RPM, for example. Okay, here. On the other hand, if we would like to know the speed in terms of radian per second, right? The synchronous speed would be 2 pi f divided by p, right? This is in, but ns is in RPM here. Okay. Okay, this is I have talked already, right? If the rotor speed Nr is equal to synchronous speed Ns, it doesn't cause magnetic induction in the rotor. The torque in the rotor will be 0. It's not possible, right? So the speed of the rotor is usually less than, a little bit less than synchronous speed. Then the motor can be operated just for under this condition. But for no load condition, Nr may be close to Ns, Nr close to Ns when no load, right? It will move very fast, right? The fastest speed of the motor is that no load speed, right? Without taking any load. But when you apply the load into this motor, the speed will drop, right? Rotor speed will drop. If you apply more loading output, the speed is drop more, okay? Then we have one index to indicate the operating condition of the induction motor. We call slip, right? Slip of the rotor. Slip means the difference in speed of synchronous speed and rotor speed in terms of per unit or in percent of speed. It means that how much the rotor speed drops from synchronous speed. Okay, so slip can be computed by Ns minus Nr divided by Ns, right? Divided by Ns here. This is synchronous speed. This is rotor speed, and if we use the term in percent, in percent is mean we multiply with 100. Okay, for example, if ns is 1500 rpm, that is maybe 4-pole motor, right? We can guess from this is 4-pole motor, and the motor is operating under the condition that nr is 1420 rpm. So the slip would be 150 minus 1420 divided by 1500 is equal to how much? 1500 minus 1420 0.053. This because this is slip value, right? The slip value, or 5.33%, right? So we, from this equation, if the slip is more, it means the motor is taking more load, right? Taking more load, more. The NR, if NR decrease, it means that slip will be increased, right? So NR decreases mean that the motor taking a higher loading level, right? Higher loading level. If we plot in power, right? NR will drop, right? When we taking more load, right? But if we plot in slip term, if the power is we take more power output, the slip will be more, right? Slip will increase, right? It means the difference between synchronous speed is increased. Slip will be increased like this here. So slip can represent the motor condition, right? If we measure the motor in higher slip, it means it's operating in higher loading condition here, right? Or we can rearrange this equation into this equation, right? NR equal to 1 minus ns, 1 minus SNS. So if we know slip, we can know NR, or if we know NR, we know slip, right? If we know slip, we can compute the rotating speed of the motor also. Okay, and slip will represent the power output of the motor. So okay, if the slip is 0, it means the rotor speed is almost equal to synchronous speed. If slip equal, it means these two values is equal. It means that no load condition, right? No load condition is maybe slip is almost 0. Maybe start from here. Slip 0. No load condition, right? But it's exactly 0. It's not possible to be exactly 0 because the speed of rotor just can be only very close to synchronous speed under no load condition, but it's still a little bit lower than synchronous speed. Okay. And in the case of slip is 1, what mean by slip is 1? Slip 1 is mean the rotor is not moving, no move, right? This is 0. NR is 0. It means that you block the rotor. You just block it. So it's or it's not possible to drive, right? It's connected to the very heavy load, very high torque, and it's not possible to drive. So slip is 1, right? So you block rotor. This is a very dangerous condition, right? If you would like to know what happened to the motor under this condition, you can try, right, blocking the electric fan in your room or in your house, right, and then turn on the fan and try to block the rotor and see what happened, right? It will cause very high temperature, and it can make a fire on your electric fan, right? Okay, while rotor hasn't rotated or stopped, the frequency of rotor equal to frequency Fe supply stator. When the motor starts rotating, frequency is depend on the relative speed. Okay. Okay, let's see some example, right? Okay. The induction motor 3-phase 10 horsepower 208 volt 4 pole 60 hertz, right? With wire connection. Slip is 5%. It means S. What mean 5%? It's S equal to 0.05, right? At full load condition. So it means this motor will operate at full load condition with the speed of ns minus nr divided by ns equal to 0.05, right? In this case, and this motor is 10 horsepower and 208 volt, 4 pole motor 60 hertz. What mean by 4 pole motor 60 hertz, right? We can compute ns, right? Synchronous speed. So synchronous speed is 120 f divided by p. We talk about this formula here, right? Synchronous speed. So 120 f by p. 120 60 hertz divided by number of pole, right? Is 1800 rpm. This is synchronous speed. Okay. Then we can compute rotor speed because we know synchronous speed and we know slip, right? Then we can compute rotor speed, or we can use this equation, right? We can use this equation here, right? For rotor speed. So then the rotor speed is 17110, right? We can see that a little bit lower than synchronous speed. The rotor speed must be lower than cannot exceed synchronous speed here. Okay. And then the frequency at the rate. Frequency of the rotor frequency at the rate. We can use Fr equal to SFE. The frequency of the rotor, right, is equal to 0.05 into 60 hertz is 3 hertz, right? Here. This is the frequency of rotor. And then the torque, right? The torque at the rated torque. The rated torque is as P output, torque shaft, P output divided by omega R. And omega is, right? Omega is a speed output, right? Output speed we can compute from RPM to radian per sec by multiply with 2 pi and divided by 60, right? 2 pi radian and 60 second, right? Second. Then it's become radian per second here. Okay, radian per round, and this is a second per minute, right? From round per minute into second, radian per second. We get this radian per second. And what is the power output? In fact, we don't know the power output, but we assume the power output equal to power input, right? And this is power output. Sorry, this is power output. 10 horsepower is mean power output. Is therefore the power output is 10 horsepower multiplied with 747 watt, right? Per horsepower is 7,460 watt here. This is power out, right? When we have motor, if it say this motor is 10 horsepower, it mean output. Here. This means power output. When you say how large of that motor, or how many kilowatt, maybe 7.46 kilowatt here. It means output, right? It's the nameplate of motor. It means output, right? The power of the motor is mean how large and how much the power to drive. Okay, to drive the load. It means output of the motor. Here, therefore, the torque is P equal to T into omega. So torque will be power divided by omega. Here, right? Then we have power out is 7460 divided by the speed, right? Omega R here. Speed will be 179.07. So we have 41.7 Newton meter. This is an answer. Okay. This is just for simple calculation of the motor, of the induction motor. Okay, so when we analyze the induction motor, so one useful techniques is the equivalent circuit techniques. The equivalent circuit technique is the technique that we analyze into R and L circuit. The motor, this motor, when we supply the electrical power into this motor, is similar to in electrical side is just similar to we supply the electric power to this circuit. So this circuit is the circuit that represent the motor, right? Represent of motor. It represent this motor here, and so it's easier to analyze because when we have the motor, we supply the power V and I. It's not possible to calculate, right? But if we know the equivalent circuit, so we can calculate how much the current flow in different part of the motor and how much the power to transfer into the output, how much the loss, right? The equivalent circuit will tell us how much motor loss, how much motor output, and how much motor torque is very useful techniques here, right? So we call this is equivalent circuit. It's not the actual circuit, but this circuit can represent the motor. Okay, so the equivalent circuit usually have 5 to 6 parameter, which is R1, X1, RC, XM, R and X of the rotor. So in the stator part here, in the stator part, it will have the resistance and inductance, right? Resistance and inductance, and then there is the loss in the core to induce to the core parts, magnetic core here. This is RC and XM representation. And for rotor, the rotor also have the resistance and inductance here, the rotor. So the equivalent circuit is represent different part of the induction motor here. Okay. Then we can rearrange the equivalent circuit. So if we have the transformer here, this is the part here, right? This is the stator, and this is the rotor part. And for easier computation, we transfer the impedance in this side to the same side, to equivalent at the same side. Then we have this equivalent circuit here, and we call this is R1 and X1 of rotor of the stator, and this is from the core, and this is the X2 and R2 of the rotor here. Okay, and S is the slip. So when the motor load the higher load, so the slip increase, right? Slip increase here. This value is decreased, the current will flow to this part more, and the output is high. So R1 divided by S is represent the output of the motor also. Output plus rotor loss. Yeah. Okay. And this part is almost constant, right? The stator and stator loss here. Stator and stator loss. Okay. So with the equivalent circuit, right, of three-phase induction, we can define the the value of the variable as follow, right? V phase is mean when we analyze this circuit, V phase is voltage per phase analysis with per phase analysis. Therefore, V phase will be V line of the motor divided by square root 3 here. For example, if we supply with 380 volt 3 phase, V5 for analysis will be, we will use 380 divided by square root 3 at V phase here, right, to analyze this circuit. So it's V line to line divided by square root 3, right? It's VL by root 3. I1, I2 is the current. Here is the current at stator. This I2 is the current at the rotor. Okay, as the equivalent circuit, right? IM is the current create its magnetic field, right? IM is here. R1, R2, the resistance of stator and rotor, respectively. This is resistance of stator and this is resistance of the rotor. And R2 by S will represent the power output and the rotor loss, right? RC is the resistance of core, right here, right? And usually RC is very large comparing to XM. So RC is very large value is can be substituted by open circuit. So we can neglect RC, right? Because it's very large value, almost open circuit. So we can have only 5 parameters for analysis sometimes, right? For approximate. So we can neglect RC. X1, Xm is the reactant of rotor and stator. Rotor and stator. Xm is the reactant here caused by magnetic field. Okay. Or we can we can separate this part, right? Separate this part into two values of the resistance. One is R2 and another one is R2 minus S minus R2, right here. Or we can have 1 minus S minus 1 into R2, or is 1 minus S divided by S into R2. And this is the loss in stator, right? R2 is the loss in stator. Therefore, 1 minus S divided by S R2 is power output, right? This is I2 square R2 is stator rotor loss. But I square into this, I minus S R2 is the P out. But in fact, we call this P air gap. Is the power that transfer from into rotor, power at the rotor shaft. But the power output must be this power, right, minus P out would be I square I minus S divided by S R2 minus the other loss for friction and windage loss, friction and windage loss, and P stay loss. This is the loss, mechanical loss, or we can call mechanical loss, minus mechanical loss. Then we get the output, right? The output would be this value and subtract the mechanical loss, right? The mechanical loss we have usually we have two types: friction and windage loss. Friction loss, windage loss, and stay loss, right? Which is small value. This is usually small, usually very small value, maybe less than 1% of the motor power. Okay. Then with the equivalent circuit of the motor, it can explain the operation and characteristic in steady state of motor. So this also helps to explain the cause and various loss in the motor easily. The relationship between power input and power output can be achieved. The power air gap, right here. Power air gap is mean transfer here, and P con is the power that convert from electrical power to mechanical power, or maybe called the internal power, P friction and windage, stay load loss, and P core loss is the number of loss, right? So this is the model of the rotor part, or as I has been write down like this, right? We can have we can separate into R2, and then this is R2 minus R2 like this, and this is a power power con, right? Power con. So from here, right, if we supply the power here, this is a power input, right? Square root TVI cos theta, or this is the power factor. If we supply our input here, right? PE, right? PE here, input here, and this is the stator loss, right? Stator loss is there. Stator copper loss is R1, the stator copper loss, and then core loss here. The power will flow here, and then this is core loss here, right? And from this, the power transfer here we call air gap power. It's power transfer from stator to rotor, right? Across the air gap, right? Power across the air gap. This is PAG here. P across here. If we compute the power across here, we call PAG here, right? How much PAG? PAG would be I2 into E1 here, right? P air gap. Okay, and then if we subtract the rotor loss, where is the rotor loss? The rotor loss is here, right? R2 here, R2 rotor loss here. Here we call P conversion, right? The power that convert into mechanical here from this. P conversion, P that convert to mechanical, right? And then this is the power to drive the shaft, right? To drive the shaft is the torque induced into omega, right? P is T omega. And if we subtract the friction and windage loss and stay loss means the loss that are very difficult to predict, but is there when the motor move, when the rotor move, there is some loss, small loss that cannot very difficult to measure, right? And then we have the output, right? Here is a P convert, and before to P is mechanical, right? We need there is a mechanical loss here. The mechanical loss is there. Okay, this is the method of analyzing three-phase induction motor using equivalent circuit, right? So if we know this equivalent circuit, so we can compute the loss in different section of the motor, right? In different section, we know how much the loss of stator, core loss, rotor loss. So we know total loss of the motor. We know the efficiency of the motor. Then, okay, if we know the power output, and if we know the speed, we can compute the torque, right? If we know power output, we know the torque, we can compute speed. So it depends on the parameter that we know and to compute. Okay, and this figure show the loss take place in different part, right? This stator loss is the loss in this stator. We use this R1 as equivalent parameter, and core loss, for core loss we use RC as a parameter. And then the power transfer, right? Transfer from stator across air gap to the rotor here, right? From this part, the power transfer here we call PAG. Here, PAG, right? Okay, and then after that we have rotor loss. And this circuit, we for clearer representation, we should say it's R2. Yes, the loss in rotor is R2, and this is R2, right? And this path is the P conversion here, right? P conversion. Therefore, P conversion is I square into this value, right? I2 square. And rotor loss is I2 square R2 is the rotor loss here. But please keep in mind that this is per phase condition, right? Per phase. It means we solve only one phase, right? Of 3 phases, right? Usually when we compute total power, we need to multiply by 3. When we would like to know total, right? The total power here. And then this value is the power that drive the rotor to move, right? And then we have the friction and windage loss, right? Which is the mechanical loss and stay loss here, right? After sharp torque power here become a sharp torque power. Okay, and this is the loss in different of the motor. In practice, we don't know inside the motor, right? In practice, whatever, don't care, right? In practice, whatever we don't care. But for analysis in research work or for motor manufacturer, we need this analysis, right? In practice, if we have the motor, we know the power output, we know power input, we know PE, and we know PM. So we know this value and this value, right? We know P in and P out, right? Maybe P in and then P out, right? So we don't care what is the parameter, right? We can compute the efficiency of the motor by P out divided by P in and multiply with 100%. So if we can measure power out and power in, that's all, right? That's all here. So this is the loss take place in the motor. Okay, but in practice we can measure this by power meter, right? By power meter we can use the meter, and this part we can measure the torque and speed, right? Torque and speed. So then we get the power out. Then we can know that how much the efficiency of the motor, or we know total loss. P loss of the motor will be P in minus P out, right? This is total loss, right, of the motor, right? In minus out is mean the loss. Usually the loss is dissipated into heat, mostly into heat. When motor operate is the ambient around the motor or the frame of the motor. When we touch on this motor, you will feel it's hot, right? It will be hot. That is the loss of the motor. Okay. Okay. Okay, I think I will take a break here and maybe let you manage some knowledge here, right? Manage some data that's put into your brain now, right? Try to manage it first, maybe, and take some rest, and we will come back. I think I will go to the next section, right, to give you some calculation example on the model equivalent circuit analysis here, right? And then we will have some example here, 3, 2, and 3, and 4, and then example 4, until to determine the Thevenin theorem. I think it's maybe until slide number 25. Maybe we will come to this slide, okay, for my lecture, and then I will, and for to get the speed torque curve characteristic, I think maybe we don't need to talk into detail in this part. and to determine the equivalent circuit also, right? But I will assign you the homework number 1. I think homework 1. Okay, I think maybe it's enough for you. Okay, let's have some break and we come back on maybe 4 o'clock, right? Okay.